So the strategy we're about to show right here is we're about to show that this square root of 2 number is irrational. Now, notice that if we are successful, that means that this entire religious obsession that ancient Greece has with numbers, we're about to throw this like up in the air because they are thinking the entire world is governed by fractions. There's no such thing to them as the number line. There are whole numbers and there are splitting of whole numbers. Like there's nothing else. So how we're going to show that this has to happen is we're going to pretend that the square root of 2 is not irrational. We're going to pretend it's rational. It's something that can be represented as a fraction. And then all we're going to do is explore that consequence. And what we're going to find out is that in that exploration, we're going to realize that this fraction is stupid. Like it doesn't make sense. It doesn't work. It is literally going to create a paradox. We're going to find out that this fraction can both be simplified, like fully simplified, and not fully simplified at the same time. That can't happen. You can't have 1/2. 1/2 is simplified. You can't make it more simple than 1/2, right? If you have a number that can be made more simple, then it gets made more simple. If you have a number that is simple, there's no more on top of the simple. It's just is. So we're going to see that for square root of 2, that's what breaks. All right, so we're going to begin. Let's imagine that we have the square root of 2. The square root of 2, we're going to pretend can be written as a fraction. We're going to imagine that it's a simple fraction. So I'm not talking about like other ways of representing it in big, complex gotcha moments. I'm just saying, can it even happen? If it can happen, then we should be able to do some natural things. We should be able to take this and multiply both sides by q, and then we would get square root of 2 times q would be equal to the numerator. That should work. In fact, on top of that, I should be able to square both sides, and I would get 2q squared equals, that's a little typo, that should be p squared. Okay? This is a natural thing. We're just moving some symbols around, right? It has to happen if the beginning thing is true. So we're just simply saying that if it's a fraction, then I could also write the fraction like this. Okay. So I'm going to go ahead and summarize up in these slides because some of these take up multiple slides. I'm just going to show us where we're at in the story. We already started like, if this is a fraction, then I can represent the fraction this way. Well, a consequence of that is that means that I've got over here 2 times a number. 2 times, whatever q squared is going to be a number, and 2 times that creates 2 times a number. Well, 2 times something makes it even. So that means that p squared, whatever this number is, has to be even because it's 2 times something. So p squared is going to be even. Excellent. So we're going to go ahead and write that down. P squared has to be even. On top of that, if I take this and I break it down a little bit, I'm going to bring it down here. We're going to have 2q squared equals p squared. I recognize that p squared is even. Also notice the only way to make an even by multiplying something times itself is that that must have been an even times an even. Like if you do 3 squared, 3 times 3 does not get an even number. 5 times 5 does not get an even number. It's got to be, I've got a 2 that's appearing somewhere as a factor here and somewhere as a factor here. So that means that each individual p has to be even, and it means that I can break this as saying I have even times even, so that even if I look at the 2q squared and I say that maybe this 2 came from this even, it still makes q squared have to be even as well. So the important thing to recognize is that through just exploring this kind of flattened structure, we're going to recognize that both p squared has to be even and q squared has to be even. And that's just from playing around with where 2 appears as a natural consequence. Okay, well, notice where we're at so far now in the story. We have said that if I can represent this as a fraction, then that means I'm able to get a number on the numerator and the denominator that are both even. Well, that doesn't work if I started and said it was simple. Y'all see that? Like if I started with this is a simplified fraction, and then I explored it and I naturally found out that it's also not a simplified fraction, I've created a little bit of a paradox here. That means that square root of 2 is a fraction that is both simplified and not simplified. That doesn't work. That can't happen. You can't be both true and false, both on and off. You cannot be a fraction that can't be simplified anymore and is also the simplest it could possibly be. It doesn't work. So what that means is that in either of these ways that we connect the dots, we either have to choose that if we allow square root of 2 to be a fraction, then it must be a fraction that makes no sense, or maybe we just started wrong and this thing isn't a fraction at all. And that's where we get the conclusion. The conclusion is that this is not a number that can be represented as a fraction, because if it is a fraction, that fraction that it is makes no sense. Like, it doesn't work as a fraction, so it must not be. Now that's eye-opening, to say the least, because now the entire world of the rationals just got blown wide open. People thought that you had numbers from things you could count, numbers from things you could split, and all of a sudden we found out there are numbers that exist that we can't even describe except for as a story. Like, think about the square root of 2. The square root of 2 is not a number, it's a story. It's saying if I could square root 2, then I would land somewhere near 1.7-ish. But 1.7-ish is not square root of 2. Square root of 2 is square root of 2. Like, square root of 2 is literally us trying to describe a number I can't touch. I can only get close to. I can only work my way towards. Like, it's only a thing that's there, but I can't touch it. People did not like that. All right, so conclusion. There must not be a fraction that represents square root of 2, because that didn't make any sense if it did. So it's not rational. We'll call it something else. We'll call it the irrational. So consequences: the moment that Hypatius found this and reported to Pythagoras and all of his people, he was promptly thrown off a ship and drowned. So he was murdered. But nonetheless, like, you can't, the ancient civilization couldn't close Pandora's box once it was opened. And all of a sudden, irrational numbers are popping up everywhere. Cube root of 2. Cube root of 2 is also an irrational number that came up as a part of ancient legend, because in a time of drought, people went to the oracle. You all know that there were like oracles that helped to provide wisdom and religious guidance. They went to the oracle and said, how do we end the drought? And they said, take the cube altar to seer, like, make that twice as large. Well, to make that twice as large, they had to double a volume. And to double a volume, you have to increase each side by the cube root of 2. And the cube root of 2 is irrational, and no one knew how to figure that out. So, like, it became a thing that started to plague society. Irrationals were not widely accepted.